Hi everyone. Last time, before we took a detour to examine more closely how to manipulate abstract functions, we were building the steps we need in order to prove that the cardinality of a finite set is uniquely determined by the set. Proving it and establishing some further statements that are equivalent to the statement that a set is finite requires a real facility with function manipulation that we didn't have. Now, after the last 3 videos, we're experts at functions, and we're ready for the remainder of our discussion of finite sets. As you'll see, what would have been very difficult to understand, now, after the last 3 videos, will be very easy to follow. All of this work is required just to prove rigorously that each finite set has a unique finite number of elements. And all that is required in order to define infinite sets. One important thing to contemplate is that we are never going to define infinite in a concrete way. Rather, infinite means a set that does not have a unique finite number of elements. That's all it means. All the mind-bending consequences of infinite sets stem from this simple fact. There is no bijective correspondence between the set and a section of positive integers. We ended the previous video about finite sets with the main result for finite sets. It doesn't quite prove that the cardinality of a set is uniquely determined, but with this theorem in hand and our new expertise with functions, that result follows closely behind. The rest of this video will be a series of corollaries that follow closely from the theorem we ended with last time. So that theorem is, let A be a set and B be a proper subset of A. Suppose there exists a bijection f from A to some section of natural numbers, then there will exist no bijection from the subset to that same section of numbers. But provided B is not empty, there does exist a bijection from B to some smaller section of the natural numbers from 1 to m with m less than n. So for the proof of this statement, see the previous video about finite sets. But from there, we can now prove the following. If A is finite, there is no bijection of A with a proper subset of itself. So assume the opposite. Assume that B is a proper subset of A and that there exists some f from A to B that is a bijection. So by assumption, there's a bijection G from A to some section of natural numbers because A is finite, and that's what finite means. So now we're going to make a composite of G with the inverse of F. Now, because F is a bijection, the inverse exists. The inverse of F is from B to A, and then G is from A to 1 to n. So because both of these are bijections, their composite is a bijection from B to 1 to n. But this contradicts what we just wrote down up here, because the theorem says that if A has cardinality n, meaning that there's a bijection from A to 1 to n, and B is a proper subset of A, then this tells us that there is no bijection of B from 1 to n. But we just constructed one using our assumed bijection from A to B. So therefore, the assumption is wrong, and there is no bijection of A with a proper subset of itself. Okay, good. Okay, next corollary, the set of positive integers is not finite. So how do we prove this? If we have a function from the positive integers to the positive integers except for 1, so starting at 2, and we define it as f of n equals n plus 1, then that function is a bijection from the positive integers to the positive integers plus 1, right? Because every integer here, we just move it over 1. So this is a bijection, and this is a proper subset of the positive integers, and therefore, from what we just said, the positive integers cannot be finite because a finite set cannot have a bijection with a proper subset of itself. So this, you could say this is a contradiction with the previous corollary, therefore the positive integers are not finite. Okay, so now here is the statement that we set out to prove when we started looking at finite numbers. The next corollary is that the cardinality of a finite set A is uniquely determined by A. Okay, so now we're in a position, after all of that, we're in a position to prove this quite easily. Let m be less than n. So suppose there are two bijections, f, which goes from A to the section from 1 to n, and g, which goes from A to the section from 1 to m. Then we can take a composition of g with the inverse of f. So the inverse of f goes from n to a, and then g goes from a to m. So the composition g circle inverse of f goes from 1 to n to 1 to m. And these are both bijections, so this is a bijection. So that means that we have a bijection from 1 to n to 1 to m. But that means that this is a bijection from a finite set to a proper subset of itself, which contradicts what we just said here. This is impossible. So what that means is this is impossible. There cannot be two bijections from a set A to two different subsets of the natural numbers. There can only be one, and this is what determines the cardinality of the set. Therefore, the cardinality of the set is uniquely determined by A, and that's what we set out to prove. Okay, so this shows why what seems like a very simple statement that, yeah, a finite set has some number of elements. This was the thing that we were talking about to begin with. It seems obvious if you have a bag with 5 marbles, but what if you have a boxcar with 10 million marbles? How do you know that there's one set number of marbles in that box? It's very hard to prove. It took us a lot of machinery in order to prove that rigorously, that yes, indeed, there is some specific number of marbles in that boxcar. There are several important results that fall right out of that fact. If B is a subset of a finite set, A, then B is also finite. And if B is a proper subset of A, then the cardinality of B is less than the cardinality of A. Now, again, this is so interesting because these statements are completely obvious, right? Obviously, if the bigger set is finite, the smaller one has to be finite too. And yet, it took us all of these steps in order to actually get so we can prove that this is true. So with all of this work we've done, we're now going to be able to expand or clarify the definition of finite. It's not actually required that B have a bijection with a section of positive integers. We can prove B is finite with less restriction than that. That's what we'll prove now. So corollary. Let B be a non-empty set, then the following are equivalent. 1, B is finite. 2, there's a surjective function from a section of positive integers onto B. And 3, there's an injective function from B into a section of positive integers. Each one of these statements is equivalent. So let's take a minute to think about what this means. So if B is finite, that means that there's a bijective function from some section of integers into B, and a surjective function from a section of integers onto B means that every element of B is covered by the numbers, so that there's no elements of B that are left over. In other words, this finite section of the positive integers is enough to point to every element. And so you can see how this means that B is finite. Because if this weren't true, there might be extra elements here that aren't accounted for by the section of positive integers. And if there's one, there could be infinitely many. We haven't limited B in any way. But if we know that every element in B is covered by some element in this finite section of integers, then we know that B has to be finite also. And then the third one, that there's an injective function from B into a section of positive integers, is going the other way. So we have B and some section, And the point here with injective is that there's only one element in B pointing to each number in the section of integers. So without this requirement, it would be possible for there to be multiple elements of B that are pointing to the same element here. So for instance, if you could have, a sine wave, and then you could just have multiple copies of B that are all pointing into the same section, right? So then this could go on forever, and again, then B could be infinite. If you allow multiple elements in B to point to a single element in the section of integers, then we haven't accomplished anything. But if this function is injective, and there's only one element in B is allowed to point to each element in the section of integers, then that means that this has to be finite too. Okay? So these three statements are equivalent. They all say that B is finite. And so the important thing is that this corollary kind of relaxes the definition of finite a little bit. You don't actually need to find a bijection from B into a section of integers. All you need is either a surjective function that goes from the section into B, or an injective function that goes from B into the integers. Either one of those is sufficient to prove that it's finite. Okay, so how are we going to prove this? So with an if and only if statement, you have to prove both ways. Assume one, assume the first, prove the second, and then vice versa. With a three-statement theorem, you have to prove them in a circle. So we assume one, prove two, assume two, prove three, assume three, prove one, and then any one of them is sufficient then to prove that the other two are true as well. Okay. Okay, so we'll start with assuming one and prove two. So the first part, this part's easy. Assume that B is finite. We need to show that there's a surjective function from some section of positive integers into B. We assumed that B is non-empty. So finite means that there exists some bijection from B to the subset 1 to n. Since G is bijective, so is the inverse, so that means that there exists a function from the section into B, which is also bijective. So let F equal the inverse of G. Bijective means injective and surjective. So F then is a surjective function from the section 1 to n onto B, and that's what we needed to prove. So that part's easy. Now we'll assume 2 and prove 3. 2 is the statement that there is a surjective function from a section of integers onto B. 3 is the statement that there exists an injective function from B into some section of integers. So we're going to assume that the surjective function exists and then prove that the injective function exists. Now, so this part of the proof now requires real manipulation of the abstract logical details of functions. And this is the moment that made me want to take a step back and go over the details of function manipulation before we attempt this proof. So now that we thoroughly understand how to manipulate abstract functions, this part of the proof should be easy. So, okay, here we go. So assume 2 and prove 3. So we're going to assume that there exists a surjective function, f, from a section of integers onto B. We need to show that there is an injective function from B into a section of positive integers. So we know that f is surjective, but we don't know if it's injective. So we cannot assume that f has an inverse because f needs to be bijective in order to have an inverse, okay? We know it's surjective, but we don't know it's injective. So we can't just start looking at the inverse of f. But we can use the pre-image of f to construct a new function, and that's what we're going to do. So let's look at the pre-image of one element of B. So this is a set of all of the elements of the domain from 1 to n that f sends to B in B. So because f might not be injective, there might be several elements in here. So this set, it's going to be a subset of natural numbers, and it's going to be some subset of the original section from 1 to n. It's not necessarily a section because it's not necessarily consecutive natural numbers, but it's going to be some subset of this set. And so that subset will have a unique smallest element. That is the well-ordering property which we proved a while ago. Okay, so we're going to define another function g from b into the section of integers from 1 to n. We're going to define it by the equation g of b equals the smallest element in the pre-image of b under f. So because f is surjective, we know that the pre-image is not empty. We know that at least one number goes into every element of b. That's what surjective means. So we know that this is defined. And from the well-ordering property, because each subset of natural numbers has a unique smallest element, we know that this is well-defined. And we've mentioned well-defined before, but we don't talk about it very much. When we define a function, showing that it's well-defined is something that we always have to do, but it usually goes unsaid. But the point is simply the vertical line test, right? If we have a relation that goes like this, it doesn't pass the vertical line test. That means this isn't a function because there are multiple values for a single element in the domain. G of b must only have one value. It's important for us to keep in mind that this is a requirement that must always be met, even though sometimes it's so obvious that we don't even mention it. But in this particular case, it's not obvious. This isn't such an obvious construction of a set. So it's important to mention explicitly that yes, G is well defined because the well-ordering property tells us so. Okay, so now we can prove that this map G is injective. To do so, we're going to use the contrapositive of the definition of injective. Injective means that if f of a equals f of b, that implies that a equals b, right? The contrapositive of that would be that if a does not equal b, that implies that f of a does not equal f of b. Okay, this is what we're going to use. So let's take two elements. If b does not equal b prime, so if we think of two of the image, the pre-image of b and the pre-image of b prime, if b does not equal b prime, then these two sets have to be disjoint. And that's just obvious from the definition of a function, because each element in A can only map to one element in B. So one element of A can't possibly be in two separate pre-images. The pre-image might have multiple values of the domain in it, right? But each element of the domain can only go to one pre-image. Okay. So A either goes to B or to B prime. It can't go to both. Therefore, the minimum elements of the pre-image of B and the pre-image of B prime must be different, right? That's, again, it's just obvious. They can't have the same minimal element because every element in the domain is in a different pre-image. And that means that with our function g, remember g is going from B to a section of natural numbers. And for each g of b, it's the smallest element in the pre-image, right? So that means that with g, no two elements of b can map to the same element of 1 to n, because gb is the smallest element of the pre-image of b. And we just said that no two pre-images can have the same smallest element. So if b and b prime are different, then g of b is going to be the smallest element of this, g of b prime is going to be the smallest element of that, they can't be the same. So that means that if b doesn't equal b prime, then g of b cannot equal g of b prime. And that means, by definition, by the contrapositive definition of injective, g must be injective. That's what we needed to show, that there exists an injective function from b into a section of the positive integers. This one. Okay, good. So we've shown that if there exists a surjective function from a section of the positive integers into b, then there does exist an injective function from b into a section of positive integers. We just constructed it. So now we have one thing left to show, which is that if there exists an injective function from b into a section of integers, then b must be finite, and that will complete the proof. Okay, assume 3 to prove 1. So assume that there exists an injective function g from b to a section of the positive integers. And we're going to call it Sn here. You'll see why in a second, but Sn just means a section of positive integers. We need to show that b is finite. Okay, so to prove this part of this corollary, we're going to use 3 facts. Fact 1, finite means that there's a bijective correspondence between b and some section of positive integers. Fact 2, if b is a subset of a finite set A, then b is also finite. If b is a proper subset of A, then the cardinality of b is less than the cardinality of A. Fact 2 was the last corollary that we did before this corollary. And fact 3, the composite of 2 bijective functions is bijective. Okay, So if g is injective, that means that there is only one element of b that's mapped to each of the elements of the section of positive integers. Now, it does not mean that every element of the range is mapped to by g. There might be some that are not reached by g at all. That's what surjective means. If it's surjective, then every element in the subset of positive integers will be mapped to. Injective means that there's only one b that goes to each one of these. So let Sn prime equal the image set of b under g. So that means this set is every element of the range that is mapped to, that is the image of some element of b. Then changing the range of g from Sn to Sn prime gives us a bijection from b to Sn prime. So this sounds weird, but it's not anything, because the range is just the set that the images of the function belong to. We can make the range bigger or smaller without affecting the definition of the function, as long as each element in the domain has a value in the range. The important detail to note here is that Sn prime is not necessarily a section of natural numbers. It's not necessarily consecutive. We don't know anything about it except that it is a subset of this set of natural numbers, okay? Because there's some could be skipped. Now, Sn is obviously finite, and the preceding corollary told us that the subset of a set is also finite. So this is a subset of this, so Sn prime has to also be finite. So the fact that it's finite means that there is a bijection from the set to some section of positive integers. It's not necessarily this one, but the fact that Sn prime is finite means that there is some section that has a bijective correspondence with Sn prime. So now we can make a composite of these two, H circle G. So G goes from B to Sn prime, H goes from Sn prime to Sm. So that means that these are both bijections, so that means that this is also a bijection from B to the section Sm. And since there exists a bijection between B and a section of positive integers, that means that B is finite. That's what we needed to show. Okay, so that was easy. So the funky part of this proof was that even though G is a bijection with some subset of positive integers, we needed to apply the previous corollary to show that this is also finite. And then, even though this itself is finite, it's possibly not a set of consecutive positive integers. But since it's finite, it will have a bijection with some section of positive integers, and then we can use that bijection and G to make a composite that will show then that B is finite. Okay, so we've shown that 1 implies 2, implies 3, implies 1, and that's it. QED. Okay, let's do one last little corollary here, and then we'll stop. Finite unions of finite sets are finite, and finite Cartesian products of finite sets are finite. Okay, so let's do unions first. So first we'll show that the union of two finite sets is finite, and then we'll use induction to prove that any number of finite sets is finite. Let A and B be finite. If either one of these is empty, there's nothing to prove. Otherwise, there are two bijections, F from A to 1 to M and G from B to 1 to N, for some choice of M and N. We can define a function h from the section up to M plus N to the union of A and B by setting hi equals fi for I up to M, and then hi equals g of I minus M for I from M plus 1 up to M plus N. Okay? It's easy to check that this is bijective, and from that, it follows then that A union B is finite. So now we can use induction to show that if the sets A1 up to AN are all finite, then their union is going to be finite as well. So it's obvious if A is 1. So if we assume it's true for N minus 1, so first we just note that the union of the sets from A1 to AN equals the union of all the sets up to N minus 1 union with AN, right? And we're starting with the assumption that this is finite, so now we just have the union of two finite sets, this one and this one, which we just showed is finite, so by induction, all finite unions of finite sets are finite. Okay, and Cartesian products go the same way. Given an element A in A, the set, that element cross all of B is finite because it's in a bijective correspondence with B, right? You just take each element of B, cross it with A, that's it. The set A cross B is the union of all of these sets, and we just showed that the union of any finite number of finite sets is finite, so that shows that this is finite. So then for the induction step, we're going to assume that A1 cross all the sets up to AN minus 1 is finite, so then we have to prove that it's true of A for A sub n. So we do it the same way we did it here. This equals, by assumption, this is finite. Now we just have the Cartesian product of two finite sets, which we just showed is finite. So that means that by induction, any finite Cartesian product of finite sets is finite. Okay, good. So we have learned a whole lot about finite sets, an enormous amount about finite sets. And with this information, now we're going to go on to look at what happens when the set isn't finite. In other words, what's interesting is, what does that mean? It only means that there is no bijective correspondence between some section of positive integers and the set. If that doesn't exist, then it means something huge. That doesn't sound like a big deal, but that means that then the set has to be infinite, which is a whole new can of worms. So we'll look at infinite sets, and then that's the last topic before we actually start looking at the definition of a topology. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.